in this last question, we can see, although you have a square root in the denominator, it is not directly associated with one out of these three categories, right? So what we can do is we can either go for a totally different technique, and we can see whether you have such a method, or else we can try to try to do some sort of a alteration for these terms and see whether we can come up with a similar term of from one out of these categories in the inverse substitution table. So for that, what we can do is we can complete the squares of the denominator, right? How are we going to complete the squares? We can write the denominator term like this one. We can write it like this, and from this term, if we can get a certain square for this term, like if it is something of this nature, we can relate it with this third category. So our goal should be to construct some sort of a square from this term. So that's basically called completing squares, right? So in other words, see, if we square this term, just forget about the middle step for a second. If we square this term, you will get this one, right? But originally we had this one. So what we do is, now this is the additional term that we will get by squaring this term, right? The reason for choosing this one to square is because then you will get both x squared as well as 2x. So this 2x is important because now we are using this relationship, right? A plus b squared is equal to a squared plus 2ab plus b squared. So in order to get x squared as well as 2x, we must have these to be equal to x plus 1, right? But the problem is then you will have this additional b squared or 1 term, right? This is the b squared term. So to counterbalance it, what we do is, we now along with this negative sign, it will be a negative 1. So if we add another positive 1, so those two things will get together and will give you 0, right? So in other words, we have not done any changes for the original term, right? We have rewritten it in a different format, right? So this one as well as this one is almost the same. Now we cannot write it like this, okay? By expecting a square, you can't just write it as this one, 2x plus 1. So this is equal to x plus 1 squared. What is the mistake that we have done here? These two are not equal, right? Here we have 3 minus this one, but here we have 3 minus this one, which is not correct, right? So what can, now here we have introduced a negative 1 as an outside term. So to counterbalance it, we should add a positive 1 as well, right? So with that positive 1, these two terms will be equal, and the advantage of rewriting it in this format is because then we can see it as a difference of two squares. And when we have that one, like, you can visualize it like this. So it is more or less the same as the third category of our inverse substitution. Okay, so now up to this point, what we have done is we have written the integral like this, right? So now we should see how to simplify this integral. The reason for changing the format is now we have this term, and so how should we use the inverse substitutions to calculate this integral? Here we should use another trick, right? Yeah, so here what we can do is, if we take now the reason why we cannot directly apply the inverse substitutions is because in the table of inverse substitutions we will, like, I'm sorry, now for this one it is not the third category, it should be the first category, okay? A digit squared minus x, right? But the thing is, here there are no coefficients for x, or you don't have things like this, right? You just have x squared. Okay, so what we can do is we can consider this one as a one full term, right? So if we substitute u as x plus 1, right, then what we can do is we can rewrite the denominator as 2 squared minus u squared square root, right? So therefore we can directly apply our inverse substitution technique, but there are some gaps, still there are some gaps, right? Okay, well, before proceeding with the answer for this integral, let me recall the previous problem that we did. That is this integral. I think we did this one in the video number 6, right? So now here also we had a similar problem, because here, although we can have a square root term, now this 3 over 2 can be seen as squared plus 9 square root to the power 3. Although we have this square root, we still have a coefficient for x, right? So what we did was we considered u to be equal to 2x. Therefore we had 4x squared plus 9 as u squared plus 3 squared, right? Then what we did was, now since this is inside a square root, what we did was we didn't rewrite the whole integral in terms of x, in terms of u, right? What we did was a little trick, right? Now as we are using this substitution, one thing that we can do is we can write the whole integral in terms of u, then the denominator will have this format. So we should use u equals 3 tan theta, right? That means now from here we can see 2x is equal to 3 tan theta. In other words, x is equal to 3 over 2 tan theta. So instead of writing the whole integral in terms of u, we just use the substitution and directly evaluated the corresponding relationship for x and theta, right? Otherwise, what we could have done was we can write everything in terms of u. Okay, so if we have this relationship, then to find du, what we can do is we can differentiate this one, which is equal to 2. That means du is equal to 2 times dx, and therefore what here we should have a 2, so we should divide it by 2, and then we will have the integral like this. X is equal to u by 2, so this is u by 2 cube, and in the denominator we will have the required term u3 squared, and for this one we have u, right? Then again now once you have this one, we can proceed with the required calculation, right? With this substitution, but instead we thought of going with the x variable only. It's like we are avoiding this step because ultimately we should convert everything back into the variable x, right? That's the reason for choosing something like this. And since here, as we have x as a coefficient multiplication with a number, everything simplified very easily. But let's see whether we can do a similar approach. What I mean by a similar approach is, let's see whether we can avoid this step and use this direct technique to evaluate this new integral. Now, by taking the same approach, we can see we can follow a very similar pattern, but the only difference we have here is that in this case we are substituting u equals 2 sine theta, and here u is equal to x plus 1, right? So you have to do everything accordingly. Okay, so now since sorry for the delay. Now since this is the equation that we use, x will be equal to u minus 1, right? That means now x is equal to u minus 1 and u is equal to 2 sine theta. Therefore, x will be equal to 2 sine theta minus 1, right? Okay, so from that we can directly convert, without using u, we can directly convert our integral in terms of, for the term of theta, with we can avoid this integral of u, right? As it was in the case of the previous question, we can avoid this step by directly jumping from x to theta, right? But you should be careful when applying the terms for x as well as for the d theta. You should be careful, right? Now, since this is the relationship between x and theta, you have to differentiate that one, and then dx will be equal to 2 times cos theta d theta, and here you have the term for x, and in the denominator you have a square root, and then you have 4 minus, this is x, right? X plus 1. So inside x you have a negative 1, and that negative 1 along with this plus 1 will get cancels out. So what remains is this one divided by square root of 4 minus 4 sine squared. Now be careful, you have a squared in here, right? See, here you have a squared term. So now you can use our familiar trigonometric terms to simplify this one a little further, right? Then it becomes this one, right? Now here, when solving the square root, you will have a modulus for the cosine theta, but with the choice of the angle, that modulus can be removed. And also you have a 2 here and 4 here, square root of 4, so those two will get cancels out. And to get from here to here, we use our basic trigonometric identity, right, which is equal to 4 times cos theta. Okay, right, now again you have 2 cos thetas in both numerator and the denominator, then ultimately you are left with this one. Okay, so the answer for this one will be equal to 2 times negative 2 times cos theta minus theta plus c, and then it's just a matter of resubstituting the original terms. Now when substituting for original terms also you should be careful, right? Now see here, this is the main equation that we use, 2 sine theta minus 1, right? In other words, sine theta was equal to x plus 1 over 2. So this is the relationship that we need to use for the right angled triangle, right? So if we have a right angled triangle, and if this is theta, and if this is the 90-degree angle, this should be the opposite side and this should be the hypotenuse. So the opposite side will be x plus 1 and the hypotenuse will be equal to 2, and therefore the adjacent side will be equal to it will be equal to the, from Pythagorean identities, it will be equal to 2 squared minus x plus 1 squared square root. Okay, and then we can say that cos theta will be equals to, from this triangle we can say cos theta is equal to adjacent divided by the hypotenuse, which is in this case the square root of 2 squared minus x plus 1 squared divided by the hypotenuse, right? And theta can be evaluated from this example, this equation, which is the sine inverse of x plus 1 over 2 plus another plus this arbitrary constant carried along the way. Okay, so this will conclude the section 7.3.